Imagine you are standing in like a million-dimensional valley.
Right. A massive, incomprehensible space.
Yeah, and you are completely blindfolded. The terrain around you is jagged, it's wildly unpredictable, and your only goal is to find the absolute lowest physical point in this landscape.
All without falling off a cliff.
Exactly, without falling off a cliff or, getting trapped in some random crater.
Okay.
And that terrifying, seemingly impossible navigation is exactly what a few lines of Python code are doing right now, quietly, in the background of your laptop.
It really is a profound hidden reality. I mean, we just type these simple commands, we hit run, and we rarely consider the geometric wilderness we are actually asking the machine to traverse.
We get so used to the utility of it. You type import torch, you build a class, the code compiles, the model trains. It just feels like plumbing, right?
Just connecting pipes.
Yeah. But today, we are ripping up the floorboards. Welcome to the Deep Dive. We are dedicating this entirely to you, the listener, and specifically, we are sending a massive shout-out to the Bus and Sigma scholars of Edward Little High.
It is an absolute honor to have you scholars with us today. You guys are exploring concepts that really sit at the absolute frontier of computational mathematics.
You are insanely curious minds, and our mission today is to push way past standard high school computer science. We are looking at a tutorial from Geeks for Geeks.
A very classic one.
Right. It's a very standard, widely used PyTorch tutorial on how to build a ResNet-18 model completely from scratch. If you have dabbled in AI, you've seen code exactly like this. It looks like standard boilerplate.
But we are going to treat this script a bit differently today.
We
are treating it as mathematical scripture. We're going to perform a linear walkthrough of the code, sure, but we will completely expound and amplify it.
We're basically translating Python into the language of Banach-Borel spaces, tensor calculus, spectral dynamics, and the theory of intelligence as pure compression.
It's going to be intense.
Okay, let's unpack this. Let's get right into the setup, the data. The Geeks for Geeks tutorial starts simply. Import torch, torchvision.datasets.cifr10, transforms.compose, and data loader.
The foundational blocks.
Right. It sets up some basic augmentations. It calls random crop, random horizontal flip, and normalize. Normally, I look at this and I just think, all right, we have a folder of JPEGs, airplanes, cars, dogs, and we're just feeding them to the GPU so it can look at the pixels.
Which is how most people see it, yeah.
But if we're really looking through the matrix here, what is physically and mathematically happening to this universe of images?
Well, to understand what the network is actually preparing to do, we have to abandon the idea of, images or JPEGs entirely.
Throw the JPEG concept out.
Exactly. We need to start thinking in terms of measure theory.
Yeah.
The raw CIFAR10 image space is a grid of 3 color channels, 32 by 32 pixels. Mathematically, it's a tensor of 3 by 32 by 32.
Right.
But in rigorous mathematics, it's not just a grid of numbers. It is a compact subset equipped with what we call a Borel sigma algebra. We are essentially working within a Banach-Borel space.
Okay, let's slow that way down for a second because Banach-Borel space sounds incredibly dense.
It does, yeah.
Let's start with the sigma algebra part. What exactly is a sigma algebra in the context of, like, a picture of a dog?
Think of a sigma algebra as the rigorous, unbreakable rule book for the universe of possible outcomes you are legally allowed to mathematically measure.
The universe of outcomes.
Right. If you want to calculate the probability of something, that something must exist in your sigma algebra. For a collection of sets to even be a sigma algebra, it has to satisfy 3 strict rules.
Okay, what's rule 1?
First, the entire universe, every single 3 by 32 by 32 image combination that could ever physically exist, must be in the collection.
So total static noise, pure black, a perfect picture of a golden retriever. Every single combination is in the universe.
Every single pixel variation, yes. Second, if a specific set of images is in the collection, its exact opposite, or its complement, must also be in it.
Okay, so if the set of all dog images is measurable,
then the set of all images that are not dogs must also be measurable.
Got it. And the third rule?
Third, if you take a countable number of these sets and group them together, say dogs unioned with airplanes, that new combined set must also be in the collection.
So it's essentially a catalog of every question we are mathematically allowed to ask the neural network.
Precisely.
If I want the network to give me a probability that an image is a frog, the set of frog images needs to be cataloged in this sigma algebra. If it isn't, the math literally breaks down, and I just can't assign a probability to it.
That is the absolute core of it. The whole purpose of a sigma algebra is to set the foundational framework for assigning a probability measure.
And why the Borel part?
The Borel sigma algebra is a specific, really vital one. It's the smallest sigma algebra that contains all the open sets of a topological space. When we say our image tensor lives in a Banach-Borel space, we are acknowledging that it has a norm.
Like a way to measure size or distance?
Exactly, a defined mathematical way to measure the exact distance between two different images and a topology that generates this Borel sigma algebra.
Okay, I think I grasped the universe part. But how do the PyTorch transforms actually fit into this?
Ah, the transforms.
Yeah, because when I write transforms, random horizontal flip in my code,
Yeah.
I'm just thinking, I'm flipping the pixels of a dog to face the other way. How does that interact with this rigid rulebook of measurable sets?
This brings us to the concept of measurable functions. When you apply a transformation, you are mapping data from one mathematical space to another.
Right.
A function is considered Borel measurable if, for any valid measurable set of outputs you look at, the set of inputs that generated them is also inside your originally defined sigma algebra.
So if my output is the set of images that have been horizontally flipped and normalized, I need to be able to trace that mathematical path backward.
Exactly. Trace it back and guarantee that the original unflipped images were already part of my measurable universe.
Then are they?
They are, and the beautiful part of the architecture is that because operations like normalization and cropping are continuous functions, and all continuous functions are inherently Borel measurable, our math remains completely safe.
Oh, wow.
Yeah, this isn't just academic trivia. If our PyTorch neural network layers and our data loader transforms were not measurable functions, the final probability output of the network would literally become mathematically undefined.
Let me see if I can build an analogy for this. Tell me if this works.
Let's hear it.
Let's say I have a giant lump of modeling clay, right? And this clay represents our initial probability measure in the input space. We don't know exactly what the image is yet. As we run it through the network, is it like pushing that clay through a highly complex, multi-layered mold so it pops out on the other side completely reshaped?
Reshaped into a probability distribution over our 10 sci-fi classes, yes.
Okay, so it gets pushed through.
That is a highly accurate way to visualize a push-forward measure. You are physically pushing the probability measure forward through the function. The network takes an input probability distribution and induces a push-forward measure on the output space.
Right, but I can only push the clay through the mold if every single piece of the mold, every transform, every layer is a measurable function.
Exactly. If there is a crack in the mold, if a function isn't measurable, the clay escapes the universe. The probability breaks.
So for the scholars out there writing their scripts, when you sit down and you type transform train and Quills transforms to compose, you are not just haphazardly shuffling pixel values to give the network more data.
Not at all.
You are rigorously mapping events across measurable spaces. You are laying the foundation so that when your network finally spits out a softmax probability at the very end, it's a statistically valid probability distribution anchored in the axioms of measure theory.
Without that Banach-Borel foundation and your data loader, your final classification would just be statistical nonsense.
That is wild. Okay, so we've mathematically defined our universe of images, and we've safely transported them to the GPU using measure theory. But they're just sitting there as raw tensors.
Waiting to be processed.
Yeah, how do we actually begin to dismantle them and understand what they are? We move into the basic block class of the tutorial. And the very first line inside the initialization is self.conv1 equals nn.conv2d. It takes in channels, out channels, kernel size 3, stride, padding. It is the ubiquitous 2D convolution.
The primary engine of modern computer vision.
Every tutorial on YouTube teaches this the exact same way. They show a sliding window.
Ah, yes, the classic animation.
Right. They show a little 3x3 square of weights, and it slides across the image from left to right, top to bottom, multiplying pixels and adding them up to find edges and textures. But I have a really hard time believing that an NVIDIA GPU is literally simulating a tiny square sliding across a picture.
You're right to be skeptical.
How are we physically and mathematically representing this four-dimensional operation?
The sliding window is a pedagogical crutch. It's useful for beginners, but it's entirely inadequate for understanding the true mechanics. To understand what the hardware is doing and what the math represents, we really must look at multidimensional tensor algebra.
Okay.
And the most elegant, rigorous way to express this is using Einstein summation notation.
Wait, as in Albert Einstein, like Relativity Einstein.
The very same. He actually introduced this notational convention for general relativity because the equations simply had way too many summation symbols.
It just got too messy.
It became completely unreadable. Einstein notation simplifies multidimensional algebra by explicitly writing out the physical indices of the tensors and implying a summation over any index that is repeated. It strips away the symbols and focuses purely on the geometry of the memory access.
Walk me through what the Einstein notation for a basic PyTorch conv-tst layer actually looks like, without getting bogged down in just reading subscripts. How do the dimensions interact?
Let's visualize the tensors. You have an output tensor, an input tensor, and a kernel tensor the weights.
Okay, 3 tensors.
To calculate exactly one single number in your output tensor, you need to know 4 coordinates. Which image in the batch are you looking at? Which specific filter or channel are you calculating? And what are the spatial y and x coordinates, the height and width?
Right, that pinpoints one exact specific value in the output block.
Now, to compute that single value, Einstein notation tells us to look at the input tensor and the kernel tensor. The kernel has its own dimensions. It knows which output filter it belongs to, which input channel it is looking at, like the red, green, or blue channel, and it has its own small spatial grid, the 3x3 offsets.
And the notation just mathematically maps these together.
Exactly. It maps the spatial coordinates of the output to the input by multiplying by the stride and adding the kernel's spatial offset. But here is the real genius of the notation.
What is it?
You don't write a giant summation loop. The notation simply states that if an index appears twice on the right side of the equation, for example, the input channel index appears in both the input tensor and the kernel tensor, you automatically sum across all possible values of that index.
So because the input channel and the kernel spatial offsets are repeated in the formula, the math implies a complete summation across all input channels and across the entire 3x3 footprint.
Precisely. No loops needed. It just defines the geometric relationship.
It perfectly defines the physical memory access. It shows how the GPU pulls from continuous blocks of memory based on these indices.
Yes, C-order contiguous blocks. But more importantly for deep learning, expressing the convolution this way allows us to compute its derivatives elegantly. And that brings us to the Jacobian matrix.
Backpropagation.
Right. During backpropagation, we need to know how the output changes with respect to the input. We need the Jacobian of the convolution layer.
Now, the Jacobian is the matrix of all first-order partial derivatives. But since a convolution without a bias is essentially just a giant linear transformation, isn't its Jacobian just the weight matrix itself?
Conceptually, yes, but its geometric structure is highly unique, because a convolution applies the exact same filter across the entire spatial extent of the image. A property upon spatial translation invariance, its Jacobian forms what we call a doubly block circulant matrix.
A doubly block circulant matrix. Okay, I need a physical visualization of that. What does circulant mean in this context?
Imagine a matrix where every row is a cyclic shift of the row above it. It wraps around on itself like a cylinder.
Okay, wrapping like a cylinder.
A block circulant matrix means the entries in this wrapping cylinder aren't just single numbers, they are entire matrices themselves.
Oh, wow.
And doubly block circulant means this wrapping phenomenon happens across multiple dimensions, corresponding to the height, width, and channels of our image.
Why does it matter that the Jacobian wraps around like a multi-dimensional cylinder? Does that actually change how the network learns?
It dictates whether the network can learn at all. The spectral properties, the eigenvalues and singular values of this doubly block circulant matrix govern the stability of backpropagation.
So it's about stability.
Exactly. If the singular values of this massive wrapping matrix are too large, the gradients compound and explode, literally destroying the weights.
Exploding gradients.
But if they are too small, the gradients vanish, and the network stops learning entirely. The structural beauty of circulant matrices is that their eigenvectors map perfectly to the Fourier basis vectors. The GPU can leverage fast Fourier transforms to navigate this spectral stability.
So when the tutorial calls nn.conv2bt, the hardware isn't sliding a cute little window. It is executing tensor algebra that maps to a doubly block circulant Jacobian, and the spectral stability of that wrapping matrix determines the life or death of the entire learning process.
Exactly.
Which leads me to a major question. If the stability of one convolution is so incredibly delicate, what happens if we just stack them? What if we string 50 nconv2dt layers together without any breaks?
That leads to a catastrophic mathematical failure. And it explains the very next line of code in the tutorial.
Let's look. Right after the first convolution, we see self.bn1 equals nn.bn2 Batch norm 2D out channels. Batch normalization.
Yes.
Now, I have always been taught that batch normalization is just a numerical hack. You calculate the mean, you calculate the variance across the batch, and you center your activations around 0. It stops numbers from getting too big and causing a not a number error on the GPU.
A very common misconception.
Right, because based on what you just said about stability, I suspect keeping numbers small is only a fraction of the story.
The idea that batch norm is primarily about internal covariate shift or just bounding numerical values is fundamentally incomplete.
What's the real story then?
To understand its true power, we must look at the spectral dynamics of deep networks. There is a pivotal paper titled Batch Normalization Provably Avoids Rank Collapse for Randomly Initialized Deep Networks.
Rank collapse. That sounds ominous. Let's define rank first. In linear algebra, the rank of a matrix is essentially the number of unique, independent dimensions of information it contains, correct?
Yes, exactly.
So if I pass a batch of 128 different images, dogs, cats, ships, planes into my network, the resulting tensor should ideally have a high rank, representing all those diverse, independent features.
Precisely. High rank means high representational capacity. You want the network to maintain a diverse feature space so the final fully connected layer can easily disentangle and classify the inputs.
So what happens in a deep, unnormalized network? Why does the rank collapse?
We have to look at the chain rule of backpropagation. In a plane network, the final output is the result of multiplying the input by the Jacobian of layer 1, then layer 2, all the way to layer L. You are taking the sequential product of many random matrices.
And mathematical literature tells us exactly what happens when you multiply many random matrices together, doesn't it?
It does, and they do not play nicely together.
Yeah.
The gap between the largest singular value and the second largest singular value begins to increase at an exponential rate. This separation is governed by what we call Lyapunov exponents.
Okay, Lyapunov exponents.
Because the top singular value grows exponentially faster than all the others, as the signal propagates deeper, all the other singular values effectively shrink to 0 relative to the dominant one. The massive matrix collapses into a rank 1 matrix.
I need to translate that into a physical visualization for the scholars. Imagine our high-dimensional data space is a giant room, right? And all our different images are scattered throughout the room in 3 dimensions.
Yes.
You're saying that as we multiply these random convolution matrices together, the room gets squashed. First, it flattens into a 2D pancake, and then it stretches and collapses into a single 1D line.
That is an excellent visualization. All the diverse variance in the data is compressed into a single direction.
But if it collapses into a single line, that means the network becomes completely blind. It maps every single input, the dog, the cat, the airplane, to the exact same point on that single line in high-dimensional space.
It does.
The output vector becomes totally independent of the actual input image. The network has total amnesia.
We call this directional gradient vanishing. The gradient only points in one direction, regardless of the data. The network entirely forgets the specific dimensionality of the images it is looking at.
That is deeply unsettling. So how does batch normalization prevent this? How does a simple mean and variance calculation stop a multidimensional room from collapsing into a line?
Well, the research proves that batch normalization acts as a computationally cheap rank preservation operator.
Rank preservation operator.
Right. It does not perfectly maintain full rank. That would require a full whitening operation, calculating the full covariance matrix, which is far too expensive for a GPU to do every step. But batch norm preserves sufficient modes of variation to keep the rank bounded by a lower limit.
Is there a specific mathematical bound?
Yes. Specifically, it forces the rank to be bounded by big omega of the square root of d, where d is the width of the network.
So even if the natural mathematics of the matrix multiplication desperately want to collapse the room into a line, batch normalization acts like a structural pillar. It forcibly props the dimensions open to at least the square root of the width.
Exactly.
How does centering the mean do that, though?
By normalizing across the batch, the operation actively amplifies the small, unique variations between the different images, while simultaneously suppressing the largest dominant variation that is trying to take over. It disrupts that exponential separation of singular values. It breaks the dominance of the top Lyapunov exponent.
I need to pause here. You're saying the code isn't just normalizing numbers for the sake of overflow. It's structurally preventing the geometry of the data from collapsing. When a scholar types n batch norm ticket, they are physically intervening in the spectral dynamics of a Markov chain of random matrices.
They are.
They are manually saving their network from dimensional blindness.
It is a profound structural intervention. But here's where the architecture gets truly fascinating.
Okay.
Even with batch normalization propping up the rank, it is not enough. If you stack 50 or 100 normalized layers, the network still degrades. The transformations are simply too chaotic. To build truly deep networks, we need the defining genius of the ResNet architecture.
The residual miracle. Let's look at it. We scroll down the basic block code, past the convolutions, past the batch norms, and we hit a single line of code that fundamentally changed artificial intelligence.
Yeah.
Out plus equals self dot shortcut.
Your shortcut.
It is literally just a plus sign. We're taking the input x and adding it to the output of our convolutions. Why is this plus sign the reason we can train 1,000-layer networks? What does addition do to the geometry?
To unpack this, we look at another pivotal paper, Transforming Rank, how architecture navigates the spectral pathologies of depth. We need to analyze the Jacobian of this entire residual block.
Okay, let's break it down.
Let's break it into two paths. First, we have the input x passing through the convolutions in real use. Let's call that the residual branch, fx. Second, we have the shortcut path, which simply passes x forward untouched.
So the output equation is f's x plus x.
Yes. Now, what is the Jacobian, the derivative of that total output with respect to the input?
Well, the derivative of the unadulterated x is simply the identity matrix I.
Exactly. And the derivative of the branch fx is the Jacobian of that complex sequence, let's call it j sub f. Therefore, the Jacobian of the entire block is I plus j sub f.
Okay, I plus j sub f. If fx contains all those convolutions in real use, we already know its rank is naturally degrading. It's trying to collapse.
Exactly. The matrix multiplications and the nonlinear real use inside the branch naturally destroy rank. But look at the other half of the equation.
The identity matrix I.
The identity matrix is mathematically perfect. It is perfectly full rank. Every single one of its singular values is exactly 1.
I see it. The skip connection is an identity highway. Even if the convolutional branch fx completely mandles the data, loses its rank, or suffers from a terrible weight initialization, the overall block cannot collapse because the identity matrix is acting as an unbreakable steel beam holding the rank up.
That's a perfect way to describe it.
You are routing the loss gradient entirely around the rank-reducing operations.
You have identified the exact mechanism. Skip connections are a brilliant workaround to intrinsic rank loss. They preserve the rank of the data manifold by carrying the gradient through an identity path that is trivially full rank. However, if we look closer at the implications of this, it introduces a profound philosophical and architectural trade-off.
Wait, if the skip connection is a perfect bypass, where is the trade-off? It sounds like an absolute win.
Think about the logical flow of information. If the gradient constantly bypasses the heavy convolutional branches and heavily favors the pure identity skip connections, what is the network actually learning?
If it skips the weights don't update. So it's not learning deep sequential logic.
Correct. You trade off rank collapse against ensemble-like behavior. Studies have shown that deep residual networks often act less like a single ultra-deep composing logic engine and more like an ensemble of shallow, independent subnetworks.
Really?
Yes, the gradient magnitude concentrates heavily on short paths that pass through very few rank-reducing branch operations.
So it's a structural balancing act. If you force the signal exclusively through the convolutional branches, the network learns deep, highly compositional logic, but the geometry collapses and it goes blind.
Right.
But if you force the signal purely through the skips, it keeps its rank perfectly healthy, but it becomes a shallow, scattered ensemble that cannot compose complex thoughts.
That is the exact tension. The architecture must balance the relative scales of the branch and the skip to dictate where the network falls on the spectrum of deep composition versus shallow ensemble.
That reframes the entire concept of deep learning for me. But it raises a very specific question about the basic block code itself. I'm looking at it, and there are two convolutions, self.con v1 and self.con v2. If the skip connection is doing the heavy lifting of saving the rank, why couldn't we just have an identity path and a single convolution in the branch? Why the two-matrix structure?
That specific detail is one of the most subtle, brilliant aspects of the architecture, detailed heavily in the Transforming Rank paper. It is designed to combat a phenomenon known as the coherent mean spike.
Coherent mean spike. Let's break that down. Where does the spike come from?
It originates from the activation function. Look at nn.RLU in the block, the rectified linear unit. What does RLU actually do to the numbers?
It takes any negative number and turns it into a zero. It leaves positive numbers alone.
Correct. Now consider the statistical mean of your data. If you have a distribution of data roughly centered at 0, and you brutally chop off all the negative values and replace them with zeros, what happens to the average?
Well, the average has to shift. If you eliminate the negatives, the new mean of the data must be a positive number.
Exactly. ReLU is an uncentered activation function. Every single time you pass data through a ReLU, you inject a positive mean shift into the data. Now imagine if you only had one matrix in your branch. You apply a convolution, then you apply ReLU, and you add that back to the identity stream. You have just added a positive spike to a specific direction in your data space.
And if I do that 50 times across 50 layers, I'm just hammering that exact same positive direction over and over again.
Yes, the mean sum grows linearly with depth. This creates a massive rank 1 mean spike. Think of it as a blinding laser beam of bias.
A laser beam of bias.
It completely dominates the spectrum of the forward representation. All the diverse high-rank representations of your different dog and cat images would be overwhelmed and converge toward this single blinding mean direction.
So even with the skip connection saving the gradient, the forward pass would still collapse into a spike just because ReLU is relentlessly pushing everything in the same positive direction.
The cross-layer correlation of these branch means equals the activation's moment ratio. For ReLU, the correlation is very high, and the spike grows rapidly. But, look at the block again. They introduce a second projection matrix conv2 after the ReLU activation, but before it joins back with the shortcut.
So the first convolution finds the features. The ReLU triggers and creates the positive mean spike. But then, what does the second convolution do to the laser beam?
It acts like a randomized glass prism.
Up-twism.
The second matrix takes that coherent, unidirectional positive mean and projects it into a new, uncorrelated, random orientation before it ever gets added to the main residual stream.
It scrambles the beam.
It decorrelates the coherent mean spike. Because of that second matrix, the positive means from layer 1, layer 2, and layer 50 do not align with each other. Instead of a single laser beam, they become an uncorrelated random walk of diffuse ambient light. This prevents the residual representation from collapsing, saving the forward rank of the entire network.
That is just brilliant. The two convolutions in basic block aren't there just to give the network more parameters to learn. It is a highly specific, mechanically necessary structure. One expands and activates, inevitably creating a flaw, and the second one purposefully scrambles that flaw so it doesn't destroy the geometry.
The components of the feed-forward block, the skip connections routing around the collapse, the batch normalization bounding the rank, the two-matrix structure decorrelating the spike, they all operate in mechanical harmony to navigate the intrinsic mathematical pathologies of depth.
So we have engineered the perfect mathematically stable block. Now we have to look at how these blocks are stacked together. Let's zoom out and look at the macro architecture, the ResNet-18 class itself.
Let's trace the flow of the entire network.
The tutorial defines 4 main stages, layer 1, layer 2, layer 3, and layer 4, using a helper function called self.makeLayer. And there's a very obvious deliberate pattern here. Layer 1 starts with 64 channels. Layer 2 doubles the width to 128 channels, but introduces a stride 2 to cut the spatial resolution in half.
Great, spatial reduction.
Layer 3 doubles the width again to 256, having the spatial size again. Layer 4 goes to 512 channels. As we push deeper into the network, the physical grid of the image shrinks, but the dimensional width channels rapidly expand. Why this specific funnel shape?
To understand why the width is structurally required to expand, we must look at the spectral perspective of the branch Jacobian again, but this time through the lens of random matrix theory, specifically the Marchenko-Pastor law.
The Marchenko-Pastor law. Okay, let's ground this. How does this law relate to our network?
It relates to the destruction of information. We established that the ReLU activation function kills all negative values. It acts as a rank-reducing mask. Statistically speaking, if you feed standard normal data into a ReLU, it will zero out exactly half of the data. We say its survival rate, denoted as P, is 1/2.
Right, half the neurons fire, half go dark.
If you apply a rank-reducing mask to a matrix, you are permanently destroying dimensions of information. The only mathematical way to ensure that the surviving submatrix remains full rank, meaning it still has enough dimensions to fully describe the complexity of the original input, is to expand the total space before you apply the mask.
Let me try to visualize this. Imagine I have a house with 10 rooms of furniture. I know that a disaster, the ReLU function, is going to randomly destroy exactly half of my rooms.
A very targeted disaster.
Yeah, but if I want to make sure I still have 10 rooms of furniture left after the disaster, I need to expand my house to 20 rooms before the disaster hits. I have to blow up the space so that the surviving fraction perfectly matches my original capacity?
That is the exact intuition, and the Marchenko-Pastor distribution formalizes it perfectly. The transforming rank paper proves that the branch Jacobian only avoids collapse and remains full rank when the expansion ratio of the network reaches a specific threshold.
And what is the mathematical ratio?
The ratio of the new expanded width to the old width must be precisely the inverse of the survival rate of the activation function. For real U, the survival rate P is 1/2. The inverse of 1/2 is 2. You need exactly a 2x expansion to ensure the branch doesn't collapse.
So the fact that ResNet expands from 64 to 128, then 128 to 256, a perfect 2x multiplier at every stage, is not just an arbitrary choice made by a programmer trying to add more parameters.
It's absolutely not.
It is the absolute theoretical minimum required by the Marchenko-Pastor law to maintain full rank through a real U bottleneck.
It is entirely dictated by the geometry of the activation function. Applying the rank-reducing activation in this mathematically expanded space ensures that the surviving directions are sufficient to span the original space.
That raises a fascinating point. What if a scholar decides to change the script? What if they swap out N Yago UU for more modern smooth activation function, like GAU or SIOU? Those functions don't just brutally chop off negatives, they curve smoothly and allow some negative values to slip through.
A very insightful question. Because smooth activations do not strictly mask data, but rather attenuate it, their survival rate is calculated differently. It is the expected value of their squared derivative.
Okay.
Because they retain more information, they technically retain more rank at smaller expansion ratios, but the fundamental law remains unbroken. Some degree of width expansion is structurally required to keep the branch healthy as information is attenuated.
Let's tie this macroarchitecture back to where we started. Measure theory. As the data flows through these 4 expanding layers, how does this affect our Borel sigma algebras? Are we constantly building new universes of measurable sets?
We are building a hierarchy. Remember that a sigma algebra represents the resolution of your information.
Right.
A very fine sigma algebra means you can distinguish incredibly specific microscopic details. A coarse sigma algebra means you only have blurred macro-level information. In a standard, non-residual network, every time you apply a nonlinear contraction, you destroy fine details, irreversibly coarsening the sigma algebra.
The network forgets the fine details of the dog's fur to learn the overall shape of the dog's leg.
Exactly. But in ResNet, as the data flows through these stages, each layer induces what we call a sub-sigma algebra. Because of the identity skip connections, the original, highly detailed information is always carried forward alongside the new abstract features.
Oh, that's why it's so powerful.
We prevent severe coarsening. The network constructs a perfect hierarchy of measurable events. It can simultaneously access the high-frequency pixel details from Layer 1 and the deep semantic abstract concepts from Layer 4.
It is building an expanding library of knowledge, but it never throws away the books from the first floor.
Well,
Wait, there's a catch.
eventually we do throw the books away, which brings us to the most contradictory part of the tutorial, the bottleneck.
The transition from feature extraction to final classification. Let's look at the code right after Layer 4. We have built this massively complex, carefully preserved 512 channel tensor of sub-sigma algebras. And then we hit this line, self.avgpool and anti.adaptive-avgpool 2D. And it gets past a 1-1, global average pooling, the great compressor.
We take a 512 by 7 by 7 spatial grid, and we forcefully crush the x and y dimensions. We just average the spatial variance entirely away, boiling the whole thing down to a flat, one-dimensional 512 element vector. We spent the last 40 minutes meticulously preserving rank and spatial geometry, just to crush it at the end. Isn't this exactly the kind of rank collapse we were trying to avoid?
It appears contradictory, yes, but it is the ultimate necessary goal of the network. To understand why we must destroy the spatial information, we have to look at the minimum description length principle, or MDL, and the information bottleneck theory.
Minimum description length. What does that actually mean in the context of our network?
The MDL principle is a formalization of Occam's razor. It posits that intelligence is fundamentally the ability to compress information.
Intelligence is compression.
Yes. The best, most intelligent model for a given set of data is the one that provides the absolute shortest possible description of that data. We measure this using Kolmogorov complexity, the length of the shortest possible computer program that can perfectly generate a specific output. Let me try to ground Kolmogorov complexity for a second. If I want to describe a perfect 64 by 64 black and white checkerboard, I don't need to write a program that specifies the color of all 4,096 individual pixels. The program is just a simple loop. alternate black and white squares 64 times per row.
Exactly.
That's incredibly short.
Mm.
The checkerboard has low Kolmogorov complexity because it is highly compressible.
That is a perfect example. Now apply that to our network. The goal of the ResNet is not to perfectly memorize every pixel of the input image. If it did that, it wouldn't be intelligent, it would just be a hard drive.
Right.
The goal is to find the lowest Kolmogorov complexity representation that perfectly explains the class labels.
So when it looks at an image of a dog, it needs to compress it into the pure abstract concept of dogness. It has to actively discard all the irrelevant high-complexity noise, the exact texture of the background grass, the specific lighting angle, the exact pixel coordinate of the ear.
Precisely. And that is exactly what global average pooling executes. It asserts that the spatial location of the features no longer matters. It says, I don't care where the dog's ear is located on the 7x7 grid. I only care that the dog ear exists somewhere in this image.
By averaging across the spatial grid, it permanently deletes the where to isolate the what.
The information bottleneck theory formally describes this life cycle. Training a neural network involves two distinct phases. First, there is an initial fitting phase where the network eagerly absorbs as much mutual information as possible about the inputs and the labels. It memorizes.
Okay, that's phase one.
But then it enters a compression phase where it actively discards irrelevant input details to improve its ability to generalize to new data.
It learns everything, and then it deliberately forgets the useless stuff.
Yeah.
But how does ResNet specifically handle this bottleneck compared to older plain networks?
What is profoundly unique about ResNet, specifically because of those identity shortcuts we analyzed, is its behavior during compression. Advanced research into information bottlenecks reveals that networks with identity shortcuts often completely bypass the initial fitting phase.
They bypass it.
Yes, and they immediately jump straight into the compression phase from epoch 1.
Wait, the architecture is naturally biased toward compression. How?
Think back to the path decomposition we talked about earlier. The network is an ensemble of paths. If a specific convolutional layer in a ResNet is deemed mathematically redundant, if it is not actively helping to compress the data into a lower description length, the optimization process can simply push the weights of that specific branch to 0.
And because of the plus sign, if the branch goes to 0, the block just becomes a pure identity mapping. It cleanly removes itself from the logical chain without breaking the flow of the network.
Exactly. The network dynamically shortens its own effective depth. It is optimizing its own Kolmogorov complexity in real time during training. It efficiently discards noise while perfectly retaining label-critical data.
Unbelievable.
And the final fully connected layer, self.fc equals nn.linear512 num classes, combined with the cross-entropy loss, takes this optimally compressed 512-dimensional concept vector and converts it into a valid push-forward measure, a proper probability distribution over our 10 CFR classes.
We have built an absolute marvel of a mathematical engine. We started with Banach-Borel measure spaces to safely ingest the data. We use Einstein's summation tensor algebra to physically extract features. We use batch normalization to prop up the rank and identity skip connections to route around geometric collapse.
We did.
We expanded the width according to the Marchenko-Pastor law to survive real U, and we used global average pooling to execute minimal description length compression. The engine's fully assembled. Now we have to turn the key. We move to the final stage of the tutorial, the optimization landscape.
The final crucible, the training loop.
The Geeks for Geeks code provides the standard loop, criterion, and n cross-entropy loss, optimizer equal optim.sgd, and then we iterate through the epochs, calling loss.backward and optimizer.step. So what is physically happening when we call backpropagation on this highly compressed, rank-preserved architecture? How does the gradient actually navigate this?
To visualize the training process, you must imagine a physical landscape. The optimization landscape defined mathematically by the loss function L of theta.
Okay, picture the landscape.
The optimization algorithm is trying to find the lowest possible altitude in this landscape, but the geometry of this terrain is vastly complex, characterized by the Hessian matrix, denoted as H equals the Laplacian of L of theta.
The Hessian, that is the matrix of second-order derivatives, right?
Yeah.
So it doesn't just tell us which direction's downhill. That's the first derivative, the gradient. The Hessian tells us the curvature of the landscape.
Yeah.
It tells us if we are standing in a gentle, wide bowl or teetering on the edge of a jagged, steep ravine.
Exactly. And a curvature of the minimum you fall into determines how well your network generalizes. We distinguish heavily between sharp minima and flat minima.
Let's break those down.
A sharp minimum is a narrow, jagged ravine. If your optimizer lands perfectly at the bottom, your training loss is 0. You have memorized the training data perfectly.
But if I bring in the test data, which is slightly different.
Mm.
My position shifts just a little bit, and suddenly I am pushed high up the steep, jagged wall of the ravine, and my error explodes.
Yeah.
Sharp minima equal overfitting.
Yes, they're chaotic and brittle. We want to find flat minima, a wide, gentle, smooth bowl.
Right.
If you land in a flat minimum and the test data shifts your position slightly, you are still basically at the bottom of the bowl. Your error remains low, flat minima are robust and generalize beautifully. Now, in deep, plain feed-forward networks without skip connections as you add layers, the Hessian spectrum becomes wildly chaotic. The landscape is dominated by sharp ravines and treacherous saddle points.
So a plane network is basically dropping you into the Himalayas, blindfolded. But how does our ResNet architecture change this geometry?
ResNet fundamentally smooths the local curvature. The residual connections, by preserving rank and allowing gradients to flow unimpeded, create massive, nearly convex regions in the loss landscape. They actively promote convergence toward flat minimizers.
Because the identity highway allows the gradient to flow cleanly from the loss function all the way back to the early layers without getting shattered and distorted by 100 uncentered ReLUs.
Precisely. And this geometric smoothing leads to one of the most astonishing empirical discoveries about ResNet optimization trajectories. Imagine the path that stochastic gradient descent takes through this landscape.
Okay.
It is navigating a space defined by millions of parameters, so it's a million-dimensional path. If you take that million-dimensional descent trajectory and apply principal component analysis to it.
PCA is a technique to reduce dimensionality, to find the most dominant, important directions in a dataset. What happens when you apply it to a million-dimensional training path?
You find that the seemingly million-dimensional journey actually takes place in an extremely low-dimensional subspace. In many empirical cases, just 2 dimensions account for 40% to 90% of the entire optimization trajectory.
That is staggering. You have a million weights updating simultaneously, but mathematically, the network is essentially just sliding down a flat, 2-dimensional piece of paper.
Because the residual architecture smooths the Hessian geometry so effectively, the optimization algorithm does not need to randomly thrash around in a million chaotic dimensions. It easily locates a low-dimensional manifold, a flat, convex valley, and simply glides down to a robust, flat minimum.
It is exactly what we talked about at the beginning. It is finding a perfectly paved, 2-dimensional highway hidden deep inside a hyperdimensional jungle.
It is the ultimate mathematical reward for all the architectural carefulness we've analyzed today. The rank preservation, the spectral bounding, the decorrelation of the mean spike, the mathematically precise width expansions, it all culminates in a Hessian geometry that allows simple stochastic gradient descent to efficiently compress the universe into intelligence.
We have to bring this journey to a close. Let's summarize exactly what we just took our Bus and Sigma scholars through. We started with a basic 100-line Python script from a Geeks for Geeks tutorial, a completely standard PyTorch ResNet-18. But we didn't just read the code. We looked through the matrix.
We really did.
We revealed the rigorous Banach-Borel measure spaces hiding inside the data loaders. We unpacked the Einstein summation tensor algebra physically executing inside the convolutions. We exposed the spectral rank preservation of batch norm and the Marchenko-Pastor width expansions necessitated by the ReLUs, and we saw how global average pooling executes information bottleneck compression, driving the network down a flat, 2-dimensional Hessian valley. I don't think I can ever look at import torch the same way again. It isn't just software, it's a physical geometry engine.
It is a beautiful convergence of pure, rigorous mathematics and highly empirical software engineering. But before we sign off, I want to leave the scholars with one final, deeply provocative thought, something to mull over as they write their next script.
I'm ready. Lay it on us.
We established that the ResNet architecture naturally biases toward optimally compressed states by pushing redundant residual weights to 0. It acts in accordance with the minimum description length principle, constantly trying to find the shortest possible program to explain the data. But if we connect this to the ultimate grander picture of theoretical computer science, is the ResNet architecture fundamentally just a physical differentiable manifestation of algorithmic probability?
Hold on. Algorithmic probability. What exactly does that mean in this context?
Many decades ago, Ray Solomonoff proved that the absolute mathematically optimal way to predict any sequence of data is to use a universal prior based on Kolmogorov complexity. You weight every possible hypothesis by 2 to the power of negative its program length. It is called Solomonoff induction.
Solomonoff induction.
It is the mathematically perfect, flawless theory of universal artificial intelligence.
But it's uncomputable, right? A Turing machine can't actually run Solomonoff induction because calculating the true minimum program length for every hypothesis would take infinite time. It's a mathematical ideal, not a practical algorithm.
Exactly. It is fundamentally uncomputable. But consider what we just explored today. If a ResNet naturally minimizes its own description length during training, and if it structurally smooths its own optimization landscape to effortlessly glide into these optimally compressed states, are we, in effect, running a computationally feasible, highly differentiable approximation of Solomonoff induction for computer vision?
Oh, wow.
When you train a ResNet on your GPU, are you not just programming an application, but approximating the universal, uncomputable mathematical limit of induction itself?
Are we just building differentiable Turing machines desperately trying to reach algorithmic perfection? Bus and Sigma scholars, let that massive concept marinate in your brain while you debug your next loss curve. Thank you so much for joining us on this deep dive into the true mathematical reality of ResNet-18. Remember, the Python code on your screen is just the shadow on the cave wall. The multidimensional math is the true reality. Keep coding, keep questioning, and we will see you on the next deep dive.